Really quickly, excuse me, I didn't quite, my pens aren't working. Lovely. Didn't answer this question. So we can see that we have a critical point at -1, 3, and we know that the concavity is down, so that means 1, -3 is a local max. So we can tell a lot about a function. We can't tell a lot about a function, but we can tell a lot about what happens around the build point. Also, important vocab. When we call it a Maclaurin polynomial, all that means is that a equals 0. So you'll see that a lot. They want you to know Maclaurin is just a Taylor's when a equals 0. And I believe Julia will be here on Thursday, at least for the A block class, to give you some fun facts about some of our most well-known Maclaurin polynomials. Okay, so let's move forward. Let's look at a couple of examples. So for homework, you're only going to do a couple of these. We're going to spend all day Wednesday just like practice building. But to kind of get you started, I'm going to suggest something. So if you're going to build a third degree, and let's see, this says a Maclaurin polynomial. So that means your a is 0 for e to the x. So here's our e to the x curve. Whoop. And we're going to try to build a polynomial that looks like that function. So I'm going to give you some suggestions. I like to give myself a list. F prime, F double prime, F triple prime, or I'll use our new notation. So it's kind of handy to keep track of stuff. Obviously, with the little examples we're starting with, they're not too complicated, but they will get a little bit more complicated. So if we're building this around e to the x, we need to know f is e to the x, f prime is e to the x, f double prime is e to the x. Oh, we love e to the x. And for each of these, we need to evaluate them at the a point. So e to the 0, 1, 1, 1, 1. I'm going to add one more piece. This is our value. Here's our slope. Once we get to the second derivative, we're going to divide that by 2 factorial. Once we get to the third derivative, we're going to divide that by 3 factorial. So these are now our coefficients. So it's just a real quick build. So this is just a suggestion for how you might want to organize your work, because that's kind of half the battle with these sometimes. So what does our polynomial look like? Let's see. Y equals, well, they have to match at the value. So our value is 1. The slopes have to match. So plus 1 times x minus a. Oh, so it's just x. Then this, our quadratic term, has a coefficient of 1 over 2 factorial. Our third, and I'm just going to leave it as factorial, has that. Now you are going to want to start recognizing that number, these numbers. 1, because this is also really divided by 1 factorial, and you can think of this as divided by 0 factorial. Because recall, 0 factorial equals 1. So there it is, and now we can use this approximation to estimate the value of e. How are we going to use that to estimate the value of e? Well, let's see. If we think of our function as being e to the x, that would mean that we're looking at f of 1. So we're going to evaluate this at x equals 1. So we're at 1 plus 1 plus a half plus a 6. So we're at 2.5 plus 0.1, 6. So we're at 2.666666666. Wow, that's pretty close. 2.71828. That's pretty good. Pretty good approximation. So we were on this curve, and we looked at where we were at 1, and you can see we're a little low, but we're pretty close, so it gives us a nice approximation. Let's look at another one. Let's look at a third degree polynomial for sine x, and now we're going to go around 2 pi over 3. So let's see, 2 pi over 3, we're going to build our function right here. And that's what this picture is of. So that you can see right at 2 pi over 3, we know that sine of 2 pi over 3 is root 3 over 2. We're right on the money. But then as we get further and further away from the center, we start to depart from the actual wiggle of the sine function. So I'm going to kind of set it up the same way again. F prime, f double prime, f triple prime, sine x, my first derivative is cosine x. Derivative of cosine is negative sine. Derivative of negative sine, negative cosine. And we need all of these evaluated at 2 pi over 3. So sine of 2 pi over 3, root 3 over 2. Cosine of 2 pi over 3 is negative a half. Negative sine of 2 pi over 3, so we're at negative root 3 over 2. And negative cosine of 2 pi over 3, we're at positive 1/2. We know this one, we're going to multiply by 1 over 0 factorial, 1 over 1 factorial, 1 over 2 factorial, and 1 over 3 factorial. So that means our function is going to look like y equals root 3 over 2 minus 1/2 x minus 2 pi over 3. Going to have to move down here. Minus, so 2 factorial is 2, so minus root 3 over 4 x minus 2 pi over 3 squared. And my third derivative, now I'm back to positive, and we're at, this is 6, so we could cancel out the 2's if we want, and so we're at pi over 9. Whoop, what am I doing? We've got, this is 6, so we're at 1/12. This is a big old plus. 1/12 x minus 2 pi over 3 cubed. So that's our cubic approximation. I want to point out this is not alternating. So alternating is only if you have plus, minus, plus, minus, plus, minus. It has to flip-flop every single time. If you have plus, minus, minus, plus, plus, minus, minus, plus, 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 minus, that is not alternating. Alternating means flip-flops every single time, like an on and off toggle switch. So if we're going to use this to approximate sine of pi, we would just plug pi in. And so we're just, when sine of pi, well, we know sine of pi is 0. And we know that we could also do it with this, and I will leave the calculator work for you to do. So we're at root 3 over 2 minus, when we plug in pi, we're left with pi over 3 minus root 3 over 4. We plug in pi, we're at pi over 3 squared, so pi squared 3 squared plus 1/12. We're left with pi over 3, so pi cubed over 3 cubed, and I'll leave you to do that on the calculator. It's pretty close to 0. Even that far apart, we're at a pretty good approximation just using a cubic. One more example. What if we had a 5th degree? Oh yeah, because we can just make these things as big and as long as we want. And now we're going to center it at 3 pi. Oh, I realized I made the wrong picture. 3 pi over 2. So we're over here. So we know it's 0 there. But so here we are. Cosine. Here's f prime, f double prime, f triple prime. Oh, I'm going to start using that other notation. So you're going to see a lot of times we get patterns with these things, especially with sine and cosine, because the derivative of cosine is negative sine, and then the derivative of negative sine is negative cosine. The derivative of negative cosine is back to positive sine, cosine, negative sine. So you can see that it's kind of a mod 4 function. You go through 4 rotations and you're right back to where you started. So we're going to evaluate each of these at 3 pi over 2. So cosine of 3 pi over 2 is 0. Let's see, sine is negative 1, but then it's positive 1. Back to 0, negative 1, back to 0. Let's see, that would be negative 1, but negative, negative 1, we're back to positive 1. Well, that's pretty interesting. So let's build our polynomial. So y is equal to our value, 3 pi over 2, 0, is just 0, so it's not there. Then we're at 1, so x minus 3 pi over 2. Then we go to 0, and now we're already on our third degree, so I'm going to just put it in here. So minus, and it's 1, but now we have to be careful because we're dividing by 3 factorial. 1 over 3 factorial, x minus 3 pi over 2. Little tiny board. 3 pi over 2 cubed. See, they match. Nice and easy. We go to the next term. It's gone again, so there's no fourth term. And we're on our fifth term, and we're plus, and it's our fifth term, so that's got to be factorial. And so we're starting to see some numbers you should recognize. 4 factorial being 24. 5 factorial being 120, so I'm going to put it in here. 120, x minus 3 pi over 2 to the 5th power. So when you have a 0, don't put it in. It's just not there. It's bad grammar to put it in. But you can see this, and oh my gosh, well, it probably makes some sense, because when you're looking at this around this point, this is really wrong that I didn't have the right graph. This is going to look, like an odd function. It's going to look like not, an even function that looks like that, but it's going to have one part going down to negative infinity and one part going up to positive infinity. So just because cosine x, we think of it as an even function, around the point 3 pi over 2 comma 0, it looks like an odd function if we were just going to narrow in on this thing. So it makes sense that we have all the odd terms, and we get an odd polynomial around that point because of what it looks like at that point. Thus the significance of Taylor's being all about the build point. This is kind of getting long. We'll have some time to flush out some details in class. So again, we would estimate cosine of pi, which we know to be -1. And we'd estimate it by just plugging it in here every single time. So you be careful with your positives and negatives. You plug in pi here, you're going to have negative pi over 2. You cube it, you're going to have a negative number, negative, negative, positive. Those are the little grimy details that you need to be careful about. But here's an important carryover from last unit. Because if you look at this, it's alternating. We know that when we made this approximation, our error would be less than the next term. So being able to see the pattern, we would be able to say the error on our fifth term is less than the next term, which would be 1 over 7 factorial times pi minus 3 pi over 2 raised to the 7th power. That is a really powerful ending to this 15-minute boring video.